So in this lecture, the plan is to talk about complex numbers. So let me just remind you, our motivation is the simple harmonic oscillator, and we'll return to this many times throughout the rest of the course. We have the mass on the spring, right? The mass is being accelerated by the spring force, and this surface is frictionless. And then we've talked many times how to derive the ODE for this equation, which is x double dot plus omega 0 x is equal to 0. And then if you guess, as usual, x equals e to the rt into this, you get that r, the exponent there, is the square root of minus omega 0 squared. And omega 0, remember, is a positive number. Square root of k divided by m. K is the spring constant. And that means you have a square root of a negative number here. And we need to talk about what that means. So that's a complex number or an imaginary number. And you probably already know a little bit about it, but I'm going to kind of give my own spin on imaginary numbers and complex numbers, and then we'll practice some techniques for using them. So what I want to do is talk about what a complex number is. And I'm going to do it in a way that is a little bit unusual, that I'm going to try to make a contact with things that you know about vectors. So you can think about a complex number as a vector just in a kind of weird space. So we're going to try to go at it that way. And then very important, we're going to talk about how to represent a complex number using two different ways to represent it. One using the real and imaginary parts, and one using the magnitude and phase. And you need to be comfortable with both of those when you're working with complex numbers. And then there's some more, some nuts and bolts operations, addition, multiplication, complex conjugation for working with complex numbers. Okay, so let's talk now about kind of motivate where these complex numbers might be seen and how can we think of them in the same way that we think about vectors. So before I start, I want to make a connection between circular motion and simple harmonic motion. So again, we're talking about the mass on the spring. And what you're seeing in the video is you're seeing this sort of peg on a turntable spinning around. And what you notice is that that if you look at the shadow that peg casts on that screen, you see it undergoes simple harmonic motion. So simple harmonic motion and circular motion are closely connected in that the shadow that is cast by something moving in a circle is undergoing an oscillation. On the previous slide, we talked about how something which is oscillating has a connection to something in circular motion. So if I project something moving in 2 dimensions, the shadow that it casts on a screen is simple harmonic motion. So we're interested in this. We're interested in this system, which is 1-dimensional. So there's no circular motion here. So you wonder, why did I bring it up? Or is there? So what I'm going to do is I want you to imagine that suppose there is some imaginary other direction of space. So I'm going to imagine an object moving in a circle. So here's the circle. And let's say this is the object, and it's going around in the circle just like on that turntable. And now imagine that our entire world, everything that we see, is like the screen in that previous video. So our world is here. Just this axis here is our world. So our world is the screen, and the object which is moving in this other imaginary direction, the shadow that it casts is what we see in the real world. So because our world is the real world, we call it the real axis. So that's what's really going on. And then I constructed this other dimension. And because that's something that I just made up, we're going to call this direction the imaginary direction, or the imaginary axis. Okay. So the coordinates in this plane of this object, it's given an x coordinate and a y coordinate, and then it has an angle theta here. And generally, we're calling the coordinates z. So z is the kind of representing the position of this object in this plane. So it's a plane. These are not like the x and y axes. These are different, right? We have the real axis and the imaginary axis. Mathematicians have a name for this, so in case you see the name, it's called the Argand Plane. Which is a way of visualizing complex numbers. Okay, so if I want to specify where this mass is, the coordinates of the mass, I give it some position x and some position y in this strange space. X is how far I go along the real axis. And y is how far I go along the imaginary axis. Okay. This should remind you of vectors. So if I have a vector A, we know it has components ax and ay, and that tells me how far I go along the x-axis and how far I go along the y-axis. So one way to represent a vector is like this. A is ax, that's the component, times a unit vector in the x direction, plus ay times a unit vector in the y direction. So these guys are my components. And then these guys here are unit vectors. Those are telling me which direction do I go. So ax is a number. It's like 5 meters. And then, you know, a vector has a magnitude and a direction. So if ax is 5 meters, it tells me x hat is telling me which direction do I go that 5 meters in. So components and unit vectors. So I can think of the position of my mass in this imaginary space in the same way. So I'm going to call this real axis r and the imaginary axis I. This is just notation I made up. So z, which is the position of the mass, could be written as x times r hat, so that's how far I go along the real axis, plus y times I hat, and I, that's how far I go along the imaginary axis. Okay? So it looks a lot like vectors, right? The idea is very similar to vectors. So we said I can think of this weird space and the position of the object in this weird space as kind of like a vector, as some component along the real axis plus some other component along the imaginary axis. But this notation is something that I personally just made up, and so this notation didn't catch on. Or I should say it's not standard. And instead, people usually write the following. They just write x and then plus I times y, like that. So this is the standard notation. But you can think of it, and I think it's really good to think of it that way, just like it's a vector. So x is some number along the real axis, y is some number that I go along the imaginary axis, and this thing here is there to tell you that I'm going in a different direction. So I'm not going along the real axis, I'm going in a different direction. We call it a complex number. So it's a complex number. And remember, I like to think of the x and the y as the components of the complex number, just like components of a vector. So let's start thinking about how to work with complex numbers. How about adding complex numbers? Well, how do you add vectors? So, review. How to add vectors. Well, if I have A has some x component x hat plus ay y hat, and B is equal to x component of B in the x direction plus y component of B in the y direction. What is A plus B? Whoops. You all know how to do this. It's a vector. And I add the x components together, ax plus bx. Whoops. The x hat plus ay plus by in the y direction. So I add the x components together, that gives me my new x component, and I add the y components together, and that gives me my new y component. Now if I think of the complex number just like a vector, I would do exactly the same thing. So if I have z1 is x1 plus y1, and z2 is x2 plus y2, and I think of x1 and x2 as components along the real direction, real components, and y1 and y2 as imaginary components. In order to add it, I just do the same thing, z1 plus z2. I keep the real components together, x1 plus x2, plus I times y1 plus y2. So no real surprises here. Sort of intuitive how to add them. How do I subtract them? Same, right? How do I subtract vectors? I do the same thing. I subtract the x components, I subtract the y components. And I could do the same thing here. So z1 minus z2, I would just subtract the components. Okay, now the thing that makes complex numbers different than vectors is that this I is actually a little different than a unit vector. So it has the same kind of graphical interpretation, but what is this I anyway? So what I'm going to do is treat it like a number, so I can just multiply things by I. And now what happens? So here's a clicker question or a concept question. So simple question. If I take the real number plus 3, so you know this is the funny plane, so this is the real axis. One of them is the real axis, one of them is the imaginary axis. If I take the real number plus 3, which lives here, so it's on the real axis, and I multiply by I, what happens? So which of these points, A, B, C, D, or E, is the number that I get if I take the real number plus 3 and I multiply by I? So go ahead and take a moment, pause the video, see if you can commit to one of these answers before we go forward. Okay, did you select your answer? Okay, hopefully it's fairly straightforward. If I multiply 3 by I get 3i, which means I go 3 in the imaginary direction. So that means I would go here to point D. So this is 3, and this is the point, this point here is the point 3i. So it's purely in the imaginary direction. And so multiplying by I moved me from the real axis to the imaginary axis. And now I'm going to make a claim to you that this is always true. And by that I mean multiplying by I is the same as rotating by 90 degrees in this plane. So multiplying by I is equivalent to rotating by 90 degrees in this plane. Okay, so now what if I multiply by I twice? So what if I took 3 times I times I? Well, what happens? I rotated it by 90 degrees by multiplying by 1i, and then if I multiply by I again, I go by another 90 degrees and I end up here, right? So this is 3 times I squared, right? Point C. But that's on the real axis, right? So 3i squared is on the real axis, but in the negative direction. So that means that 3i squared is minus 3, right? Because the point C is just minus 3 units in the real direction. And the negative minus 3 units in the real direction. And that means that I squared is equal to minus 1. And I is equal to the square root of minus 1. So that's an imaginary number. No real number. You can't take the square root of a real number, or of a negative number. But this I has an interpretation of the square root of minus 1. Okay, so now you have the knowledge that I is the square root of minus 1, and that multiplying by I is a rotation by 90 degrees in the complex plane. And using that fact, we can now do some more algebra with complex numbers.